PWM is a standard way of describing signals with intermittent transients that we call pulses. The pulse width is the length of time the signal is active, and the period is the amount of time for the beginning of one pulse to the occurrence of the next transient. The duty cycle is a ratio of the pulse width over the period and is typically communicated as a percentage and can vary anywhere from 0%, which would represent no signal presence, to 100%, which would be the same as a straight DC signal. The pulse repetition frequency is based on pulse width and the period and describes the number of pulses that occur per second and is measured in hertz. Across all industries and applications, pulse widths and periods can span across several orders of magnitude and can vary anywhere from seconds to milliseconds, microseconds, nanoseconds, and beyond. The duty cycle and PRF are both important and useful pieces of information used to classify and describe signals, since there are an infinite or near infinite combination of pulse width and period. The two main classifications of pulse shapes are the rectangular and exponential pulse, and the average power in watts for each can be calculated using the following formulas. For rectangular pulses, Vp represents the peak voltage drop condition across the element, Pw is the pulse width in seconds, R is the ohmic value of the resistive element Vp is dropped across, and PRF is the repetition frequency in hertz. I'm sure there are other ways of showing this expression. This just happens to be the one I work with routinely. For exponential pulses issued from capacitive discharges, we'd use the RC time constant tau as part of the formula for average power. In our discussions with customers, by and large, the rectangular pulse train is the more common calculation, and it's worth mentioning that there are ways to use mathematical transformations to convert what really is an exponential pulse into rectangular pulses for ease of use and other calculations down the line. But that's not something that we need to go into here today, but this is just a transformation that is also fairly routine. What might already be clear to you, or hopefully will become more clear as we progress, is that it's entirely possible for two vastly different signals to have the same average power. A signal with a very high peak voltage and very low pulse width having a duty cycle below 1% could have the same average power as, let's say, a signal with a more traditional 50% duty cycle square wave at a reduced peak voltage with longer pulse width intervals. An average power quantity by itself tells us very little, and while I can't say it's meaningless, it really only has utility when taken into consideration along with the other quantities of pulse width and duty cycle, or PRF. Pulse signals are ubiquitous across digital electronics and are the basis of all the wonderful consumer electronics that we routinely interact with. A short list of what I tend to think of as classical pulse applications is on the left-hand side. Higher current applications manifest in LED dimmers, and PWM motor control allows for precision movements in more applications than we have time to discuss. On the right-hand side, we also likely have a short list of modern applications that can and do utilize high-power, low-duty cycle pulses in order to operate. Each of these represents an entire area of specialization and, as you might have guessed, are sensitive. Pulse shaping is used to tune an output pulse precisely to the input impedance of some other network so that it might operate at something resembling steady state. At that point, one view might be that the injected signal itself is an impedance. VCSEL drivers are used in applications related to object recognition and tracking, and is part of the principal technology that make LiDAR possible. Wideband digital communication systems using ODFM make it possible to communicate in environments where heavy signal pollution exists and have many schemes for error correction and ensuring timely delivery of voice, video, and data. As of 2022, both thick film and thin film might be considered mature technologies, but like everything else, they continue to evolve with advancements in materials, tooling, and capabilities. Thick film resistive element thicknesses are measured in microns and generally have 200 to 500 times more volume than their thin film counterparts. Thick film processes control resistor value with the deposition of a designed geometry containing different proportions of a conductor and non-conductor that in most cases are trimmed up to a desired value by laser ablation. They're hermetically sealed with a passivation glass for protection from moisture and other damaging elements that can be present in the air. Thin film passive resistive components control value mainly with geometry and exposure time to the material sputtering process. They can be trimmed, but generally aren't. They're produced in large quantities of standard values and may use passivation epoxy instead of a glass. In applications where there are non-magnetic requirements, commercial thin film parts containing ferro-resonant terminal barrier material nickel can't be used. Customers find that thick film parts are offered with non-magnetic platinum silver with or without an optional choice of lead-free or leaded solder. Thick film tends to be more suitable in application areas where power integrity is a factor of success, and thin film is more suitable for application areas where low signal or low phase noise requirements are present. In matching or feedback networks that are expected to undergo thermal cycling, thin film parts with low thermal coefficient of resistance can help keep signals stable across wide temperature ranges. Some of the challenges designers face everywhere is knowing when to prioritize a part for selection when competing properties arise, given a set of design goals and constraints. The answer to so many questions in this field begin with, well, it depends. Since 2010, the number of customer requests about using parts in what ultimately ends up being an LDC pulse application has no precedent before this period ending in 2010. As new technologies and applications were developed and evolved, it would seem that so too did the nature of the word pulse itself, and with this evolution it would seem that it might be appropriate for assumptions to evolve accordingly. A pulse could now be anything from a single transient that occurs only when the power switch is flipped on, to a condition that occurs infrequently but predictably when a signal is keyed for transmission, to a continuous square wave operating in quadrature, all the way to a device that uses LDC signals and everything in between. We see specific requests about specific pulse characteristics as they apply to our parts whenever it's a resistor, attenuator, or splitter. We see veiled requests where a minimum of information is relayed, usually in the form of average power only, or a signal initially communicated to be a 50% duty cycle with a frequency in the low megahertz range, but then may ultimately turn into a reactive request for a recommendation based on LDC conditions if parts begin to fail during testing. There are some consistencies surrounding issue reports and damaged part photos that we can share, and these are generally for resistive elements 10 to 200 ohm, but the highest concentration of interest is centered around 20 ohm. Rise and fall times are fast and consistent with MOSFET switching times below 20 nanoseconds. PRFs can change from a few hundred hertz to 10 kilohertz and are generally in the kilohertz range. Like we said before, duty cycles are low, and that can be below 1% with pulse widths below 1 microsecond. Some common observations made during our own part testing was this characteristic value drift expressed in the literature and by customers. If a part is hit with a signal for a given period of time and the DC ohmic value drifts downwards, this is definitely a sign of damage. Continuing to operate with the same properties of pulse will eventually cause the value to go up in the opposite direction exponentially until eventually, due to the rapid nature of these failures once they begin, it can take some time or even a little bit of luck to catch them in the act of changing values. This is especially true if the PRF being used is above a few hundred hertz. When this was all coming about over the last several years, we noticed that most parts we saw that failed under pulse didn't exhibit the same kind of cooked look as parts that failed due to thermal overload in the absence of proper thermal management. Lower ohm value resistors and pi attenuators with lower dB values can be subject to reasonable enough sounding average power, but due to the chemomechanical changes imparted to the part by the impulse, the part suffers a fate similar to death by 1,000 cuts. The current hits a natural choke point at the trim, and current crowding translates to regions where sharp heat flux densities produce temperature rises above what can be measured easily without thermal imaging optics with high-resolution zoom. Part of the fire and glass can refire, fuse, or ablate. Now there's material missing, and on the next pulse, the choke point has an even smaller CSA, causing the next micro region to fail. As you can see, this occurs successively and quite rapidly under the conditions customers can use. Below the critical value of resistance based on case size, it's entirely possible to make a part fail cold with no appreciable temperature rise. Even though, for example, aluminum nitride has a thermal conductivity rating of 170 to 210 watts per meter Kelvin, it's the film that can pay the price, and the film really doesn't care about average power. On the other hand, if a stable setting can be reached for the film, using a component made from a more thermally conductive substrate can contribute to reducing risk, especially if the heat generated doesn't only pour back into the traces. Terminal configurations exist that are different from the standard wrapped SMT part and can offer excellent thermal sinking benefits if used mindfully. What data is useful for qualifying parts for a pulse application? The prevailing method is to constrain the signal's average power to the component's free air rating at 70 degrees C and adjust the width and duty cycle to arrive at appropriate combinations for usage. In circumstances where pulse data is available for either a single pulse event or for a continuous pulse application, the data generally takes a log format as seen here. The x-axis denotes the pulse width, and the y-axis indicates the power for the duration of the pulse through a representative ohm value. Each case size has its own curve, and it follows that curves appear higher on the power axis as size increases. It also makes sense that the max condition for power is also higher for a single pulse event compared to a continuous pulse application. Here, a designer is expected to locate the intersection of pulse width and power based on their own application and a given case size. If that point of intersection appears below the corresponding line on the datasheet, it's reasonable to infer that there's a low risk of using the part at those conditions. IMS's conductive power ratings make assumptions about the maximum safe film temperature operating at 150 C, as well as a steady state heatsink or ground plane that's maintained at a few different temperatures. The resistor element size, substrate, thickness, and area of contact with the sink, along with the heat transfer constant of materials, provide a mechanical model for how much heat transfer potential a component as a package can have and deliver to the installed surface. D ratings are applied to account for trim depth and how materials' heat transfer constant decreases with rising temperature. One final D rating is then applied for additional safety. From there, a designer would then calculate or simulate whether or not the PCB and via array being used are appropriate from a thermal management standpoint. Just because an 0603 resistor on aluminum nitride will dissipate 13 watts in one condition doesn't mean it will in all conditions, including pulse average power. When IMS or other vendors provide conductive ratings, the assumption for signal is going to be either direct current or continuous wave. We've already mentioned free air ratings at 70 degrees C as being useful, if not somewhat limited metric, when considered only by itself across all possible combinations of resistor value, voltage drop, and pulse width. Free air ratings can be found on datasheets going back to the dawn of resistor construction. The area of the element in contact with 70 degree air is assumed to be the only factor for cooling. In a conductive heat application, customers routinely use parts above their free air rating. This is a summary slide of the major standards I could find used in classifying SMT resistors for pulse and overload conditions. IEC 60115-1 covers the generic specification for fixed resistors and detailed specs for thin and thick film resistors respectively. There are OL or overload appears to be similar to MIL PRF 55432 at a glance, and parts are tested at 6.25. They are rated power for short durations measured in seconds. Stability classifications then dictate the class of the lot based on drift. PEOL, that is, periodic electric overload, looks for a max drift of 1% plus or minus 50 milliohms as a passing criteria. Here parts are subjected to 15 times the free air rating for shorter durations of 1/10 of a second, with a few seconds in between to normalize temperature. Single pulse high voltage overload uses two waveforms for surge ratings, 1.2/50 microseconds and 10/700 microseconds. In each case, the first number is the front time and is the time for the peak current to be reached, and the second number is the fall time and is the amount of time for it takes the pulse to reach 50% of the peak. The actual power applied is a function of classification. Maximum load for continuous pulse is a lifetime aging using representative values and sizes for testing. Pulse lengths range from 100 microseconds to 100 milliseconds, and drifts in the range of 0.5% to 4% are used for characterization. I present this slide to demonstrate how many different types of testing and classifications related to pulsing and surging in resistors exist. I won't say that I'm an expert on these standards, so please go easy on me if I missed something. If the number of different tests tells me anything, it might be that one size doesn't fit all. We know that there are some factors to pulse durability, and it's natural that element size is one of them. Length is the contributor to max and working voltage, and width contributes to max power. Ohm value and chemistry are related and have a large impact, since the grain size, dispersion, and proportion of conductor and non-conductor play a role in the paths current will take. The trim style has a large impact, and in general can also account for the largest lot variance when a commercial plunge trim is applied. For a commercial part that's plunge cut, it could go as deep as 70% through the width of the element. This is also the region heat will pool first and has the highest temperature gradient. A depth-limited scan cut has the effect of normalizing the inevitable hot spot across a longer region and has positive effects that appear in all sizes. Guard bands during production limit the trim depth to 50% max. Our own limited tests show that lower ohm parts with scan cuts in LDC signal conditions can survive without drifting value, with an increase in average power above what the standard part can survive. How much a scan cut can increase survivability varies from one case size and value to the next. For plunge versus scan cut, 20 ohm, 2512 size alumina parts tested with pulses whose voltage did not exceed the maximum continuous working voltage of 200 volts. 100% of the scan cut samples were able to withstand a 2-minute test with a 4-watt average pulse without any drift, while 100% of the plunge cut parts failed with a 2-watt pulse. PRFs varied from 2.5 kHz to 7.5 kHz, and pulse widths varied from 250 to 500 nanoseconds. When considering all these different factors of pulse durability and testing methods, certain questions tend to arise. When looking at continuous pulse data, what's the relationship to lower ohm values and shorter pulse widths? It seems dubious that pulse test data for 100 ohm part, which saw minimum pulse widths of 100 microseconds, could apply to a 10 ohm part, seeing pulse lengths of 100 nanoseconds, case sizes being equal. We would agree, since film chemistry for a 10 ohm part is different enough to matter, even if the calculations translating one signal to another are spot on. What about PRF or duty cycle? Is there equivalency across continuous pulse data, knowing that a PRF might be 10 Hz or 10 kHz? Based on our investigations, not really, but not for lack of attempts made. How do I know if my pulse will work using a particular part? The deeper we go into the literature on this topic, the more we see the same recommendation. To know, you must test. Is it possible for a pulse's average power to exceed the convective power ratings? Depending on the pulse and part features we've been looking at, and how finalized the PCB layout is, yes. And some recommendations we've already hinted at will be discussed further, along with some other possible approaches next. If a signal is a pulse of any kind, low to medium duty with pulse lengths of any duration and supporting a power-related function with rise times in the nanosecond range, absolutely specifying a depth-limited scan-trimmed part should be a first requirement at a minimum. Furthermore, it's possible to design a low dB pi attenuator suitable for pulse applications that makes use of scan-trimmed or fire-value series resistors. For a pi pad, the series component is often the smallest and will have a low value, and by definition it takes the brunt of the force when its designed attenuation is low. It follows in principle and in practice that passive networks like attenuators, whether they're an integrated component package or constructed with discrete elements, can benefit from this low or no trim approach. When there's no other option for element values under 50 ohms operating with worst case LDC intervals, if circuit simulations predict that a wider resistor tolerance approaching that of 10 or 15% max could be managed, it might be possible to order a fire to value part with no trim. If this ends up being the approach, it's probably a good idea to have it designed in early. IMS routinely produces parts that have an electrically isolated center strip designed for sinking heat directly downward to a ground or thermolator using plugged vias. In the case of a pulsed resistor, we can think of no better way of managing the onslaught of rapid and sometimes damaging thermal transients. A very classic and often employed but no less relevant approach customers use is just to use more parts in parallel or series to get them up or down to the resistance they need. Once average power of the pulse is above the convective rating of the part, thermal management becomes more important. Using parts with a higher thermal conduction rating can help, but only if the heat has somewhere to go. Changing part substrates without other measures may not help. In trying to work out all of this current and ongoing research, IMS has invested in tools and instrumentation to test parts at various high-risk conditions. Aside from expensive lifetime or aging testing, some experience has suggested that a few shorter tests on parts can be good indicators of longer-term stability. The following test represents one possible method to rule out or advance a particular manufacturer part number for your LDC signal, and it assumes that you've already got a pretty good idea of what pulse signal characteristics you intend to use. If parts have trims, it's prudent to choose parts that have the deepest trims first. A test setup with no or minimal conductive heat management techniques should most closely mirror the free air rating condition, but in reality, traces do contribute to some degree. For us, cold failures occurring under 10 seconds represents the most frequent time interval for catastrophic failure. After that, generally speaking, the second most frequent interval where failure occurs seems to almost always be under 2 minutes. For sizes 0603 to 2512 in our environment with our test setup, it seems that if a part can remain stable at 2.5 times the intended average power for 2 minutes, they shouldn't yet be ruled out. By stable in this case, I mean having less than 50 milliohm value change from the starting value after 2 minutes. When looking for changes this small, probe placement has an effect, and we had good results using 4-wire probes on an HP 3478A meter. Using your desired voltage across and duty cycle, calculate an average power that's 2.5 times higher by increasing both pulse width and duty cycle by some amount. A contribution of about 1.25 times increase in power for each parameter is a good starting point. After 2 minutes of testing, plus some additional time to normalize sample temperature, if any one of the values have gone down, voltage is likely too high for the part considering the ohm value and element geometry. If values have gone up by more than 50 milliohm, and I mean for any single part, replace that part and reduce PRF and pulse width so that the average power is lower. A 10 to 15% decrease in power per iteration can be substantial. If you're able to get to the 2-minute mark and all parts reveal no value shift greater than 50 milliohm, do one more 2-minute test on the same parts once temperature has normalized. My experience has been using groups of about 5 to 10 parts, and if none shift the first time, there seems to be little chance any will shift after a second minute round. I only say this because it hasn't happened to me, but shouldn't be ruled out. Finally, dividing the average power successfully used during this 2 minutes twice test by 2.5 could be a basis for continuous operation, and setting that lot aside for further evaluation is recommended when using this method to help qualify parts for an LDC application.